welcome to our PLANQK webinar this afternoon, Quantum Workflows. I'm particularly pleased to welcome Sebastian Wagner onto our stage today. Sebastian is lead of quantum service integration here at Kipu. My name is David Niehaus. I have the honor of being the moderator of this webinar. And as you know, our mission at Kipu is to enable quantum now. And one of the aspects that we have to address here, of course, is how can users of quantum connect both classical as well as quantum-based workloads. And of course, workflows is an opportunity to do that. I'm very excited about the new developments that Sebastian is going to present to us very shortly. Allow me a couple of final remarks. We will be recording this meeting, but your names and so forth will not be shown, so no need here. If you have any questions, if you have ideas, if something has been unclear, please do not hesitate to reach out via the Q&A tool or the chat. I will be monitoring both tools, and I will interrupt Sebastian when I think it is suitable to ask your question. You're more than welcome to ask your question when it arises. So please do not wait until the end of Sebastian's presentation and demo. Feel free to do that right away, because that way we can also enter the discussion when it comes up. Yeah. So I hope we have now clarified all the administrative remarks. And without further ado, Sebastian, stage is yours. Looking forward to your presentation and demonstration.
Thanks, David, for the introduction. So also welcome from my side. I'm happy that there are so many attendees here I hope we will have a fruitful discussion also about this topic, about quantum workflows. And yeah, so as David already indicated, the goal of the seminar today is to talk to you about quantum workflows in a way, why we, or maybe also you, need them. And after we covered the theoretical part, we will also have a short demo. I will show you how you can use quantum workflows with PLANQK. And so here's the agenda, actually just what I just said. Before we dig into the workflow topic, because I'm not sure if everyone is familiar with PLANQK, so I will briefly also discuss PLANQK services, tell you what they are doing, what the purpose is, because they are an important prerequisite for our quantum workflows, which we will cover today. So then let's start right away, if there are no remarks, questions. So at Kipu, we had the issue that we had our quantum algorithms in our Jupyter notebooks as Python code and so on. And the problem was that we can't give them away to our customers because their algorithms are our IP. Another problem is also, of course, that our algorithms need a certain runtime environment to work. So it's also, even though it would be possible to ship them to the customers, we still need to set up the environment, to make them run, to set up the classical resources, etc. So that's the reason why we were thinking, okay, how can we make our algorithms accessible to our customers without giving the IP away, and also how we can enable you as potential users of the PLANQK platform to do the same. So we came up with the ideas of PLANQK quantum services. And what are PLANQK quantum services? So in a nutshell, these are algorithms which are deployed on the PLANQK platform, which have a dedicated API and can be consumed by your customers, for instance, or by our customers through this API. Yeah. So in the center of all this is the PLANQK platform. Yeah. And so you, as PLANQK, as quantum developer, you provide quantum code, and we offer you tools, a set of tools, really easy to use tools that enable you within a couple of minutes to spin up your quantum code as services. And these services are running on our platform, and this has the advantage that they can use the classical resources on our platform, look like CPU resources. We even offer GPU resources. As you know, this is also important to many problems to solve. And we also offer you via the platform access to different quantum backends. That means your quantum algorithms, which run as service on the platform, can easily switch between different quantum backends depending on your problem, etc. Yep. So, and this frees you of the burden to host code. Yeah. And it frees you also of the burden to take care about operation. You can simply deploy or publish them, and our customer and your customers or your potential customers find them via our PLANQK marketplace, and they can use it right away, even if they don't have that deep expertise in the area of quantum computing and just want to use it because to solve their business problems. So what you can also do is we also offer for the services metering and the payment. That means you can, for instance, create your service and say, okay, when my customer uses my service, I also want to get reimbursed for the costs at least I have. Maybe I will also want also to make a small revenue. So you can define or specify for each of your services how much that their usage costs. Okay, and how can you, and I already indicated this, how can you use these services? You can basically use it from your website. You can also, again, use it from your Jupyter notebook or integrate it easily into your traditional application domain. And these you can deploy your own algorithms, and of course, we at Kipu we also provide our algorithms in our on our PLANQK platform. Yeah. So one of the most prominent candidates or the most prominent algorithms is the Kipu's biosphere digitized counter adiabatic quantum optimization, or short ISCAI. Oops, sorry. And this algorithm is what it does. It's actually it solves optimization problems. That means it takes a problem in a Cubo or Hubo format and solves them. And this algorithm uses counter-adiabatic measures or counter-adiabatic terms to shorten the circuit depth and to reduce the gate count, so that we can solve the problem in a shorter time, which in turn improves the solution quality a lot. Yeah, for instance, we also need, with our algorithm, you don't need error code, no error mitigation, or it can be reduced significantly. And we made experiments where we, for instance, where we solve problems with 156 variables on IBM hardware. That means we mapped each variable to a qubit on the IBM hardware. It's also possible to use this algorithm, our ISCAI service in with IonQ or other backends. Yeah. And this ISCAI service will now play also important role for our use case scenario we are using for demonstrating and for illustrating the need of quantum workflows. So this case study, or this is air traffic control management. This case study will serve now as the running example for the rest of the slides. And as you know, I mean, some of you, like me, probably goes from time to time to flight radar and know that, yeah, the European, US, and also Chinese airspace is quite heavily congested. Yeah. So, and this, of course, reduces flight delays. And the objectives of the air traffic flow management, of the air traffic controller, is to optimize the flight routes. So of course they must be optimized. I mean, they're intersecting flight routes, as you see here in the graphic on the right, and they're intersecting. So they have the airplanes to keep the safety distance have to fly in different altitudes. Now you can say, okay, now let's simply let's fly all airplanes at different altitudes. Sky is big. But of course, there are certain altitudes which are optimal concerning fuel consumption. So basically, you want each and for economic reasons, you want each and every airplane to be basically when they are cruising on the same altitude, but without having the danger that there's a collisions. So you need the optimal usage of these vertical corridors. Yeah. And as you can imagine, this is a optimization problem, and we can formalize this problem as a graph coloring problem. So we basically, I don't want to go too much into details, but it's that you check for the intersecting routes and transform these intersecting routes into a conflict graph. And this conflict graph, in turn, then transform for a colored graph, which can then be optimized. Yeah, and there our ISCAI quantum optimizer come into play, the service I was discussing earlier. So with this ISCAI quantum optimizer, we can solve this problem. So, and as I also said earlier, like this, the optimizer takes either Hubo or Cubo formulations of problems, and of course the flight routes of the air traffic control, they are probably not natively Hubo formulations, so we need to transform them into Hubo. And before, of course, we need to load them from the database or the data store of the air traffic control. Then we need to solve this, and the result also the hopefully optimal results need to be transformed back to into flight routes, and also to be sent back to the database or stored back in the database of the air traffic control. So you see, they're different. It's not just the quantum part. There are a lot of supporting steps required. And these supporting steps can be, for instance, realized by services. And for instance, services that are either deployed in some data center or at the PLANQK platform. Yeah. Okay, and now this is a classical integration problem actually, which we in the IT were struggling with since ages. It's how do I get the data from the flight planning system, for instance. Yeah, so you need to connect to the system. You then of course the flight planning system and my service, which for instance does the Hubo encoding, does not use the same programming language. So you need to perform this integration. And why we already addressing this by making services, our quantum algorithm to services, because as I mentioned before, when you transform with PLANQK quantum algorithm to a service, it has a dedicated interface. These are standardized REST interfaces, which can be used for simplifying integration with external systems a lot. Yeah. So this is covered by the services, but you also need to orchestrate the supporting services. That means the service which implementing loading the flight routes, the service with encoding the Hubos, the ISCAI solver, and then also the service which stores the flight routes. All these services need to be orchestrated. That means executed in a predefined manner. And this can be done, of course, in different ways. So the naive way would be, great, that you use your Python program to do this. Yeah. So you write a Python program and orchestrate these services. Yeah? So, but then you have to deal. It's possible, of course, but you have to deal with a lot of idiosyncrasies and complexities, even in the time of white programming. So that means you have to, for instance, implement the service calls. Yeah, that, for instance, the ISCAI solver is called in the correct way. So these service calls has to be resilient. It means if, for instance, one of the services is dead or crashed for a certain amount of time, then you need to still be able to recover from this. Then the next thing is, in our example, and in general, quantum experiments in general are really long running. Yeah, these are the queuing times. The classical parts are often long running. If you think, for instance, quantum machine learning, so we need to persist the state, and we need to recover to the state in case, for instance, my application crashes. And again, you can do this with Python, but this needs to be all implemented by you. Then what happens when the algorithm crashes, like, or my application crashes? Then I need to recover. Then I imagine you have you made maybe on IBM's or Quantinuum backend a very expensive calculation which cost you several 10,000 euros. When the service recover, then you need to ensure that the data from this calculation are still available. Another thing is also scalability. Imagine you offer a very successful application, or very successful implement a very successful business scenario. Then also your application has to scale with the demand. And the next thing is also code is more difficult to communicate and more difficult also to understand by external stakeholders. Yeah, for instance, as Kipu, we learned, like most of our users, the quantum algorithms are physics. So they have programming skills, no doubt, but they are limited because they want to focus on the physics part and not become software engineers. So this makes it harder to communicate just via code and also to extend code. And another thing is also when we talk again about the long-running nature of quantum experiments, then you also need to introduce a certain kind of monitoring to see intermediary results, to check if you are still on track, and so on. So, and to make a long story short, this will cost you a lot of time and effort to implement this with your favorite Python framework. So what can we do? We want to use workflow technology to solve these issues. Workflow technology exists since 20 to 30 years, I guess. And I think, these workflows, actually what they are doing, workflows are orchestrating, that means are made for integrating different programs to work together. Yeah. So like in our example, for instance, to implement this use case, this air traffic use case. So, and in the next slides, I will discuss with you the advantages of the workflows, how they address the shortcoming I just mentioned, for instance, the shortcomings which you have when you implement your orchestration with Python. And the flow, or the development flow with workflow, is the one depicted here. So first, you either develop a quantum algorithm, or you develop provide a quantum algorithm or classic algorithm as PLANQK service. Then you design, and then in next step, you use the services as steps in your workflow. Yeah. So a workflow is really a low-code implementation of the service orchestration. This will be completely on the next slide. After you designed your workflows, after you defined the steps and the order in which they have to be executed, you can expose the workflow again as with the PLANQK platform as PLANQK service. So it can be called again from external IT very easily, and could be also in turn used in the workflow again. And when the workflow is executed, workflow technology offers you more comprehensive monitoring capabilities. Yeah. So, for instance, you can see, okay, the state in which my workflow is, the data, which, for instance, if just let's assume just the Hubo was created, so we can check, okay, how does the Hubo look like? Do we need maybe to do corrections before we go on with the execution on a real quantum backend, and so on? Right? So you can really monitor the inherent capabilities of workflows, that you can monitor the execution state of your workflow, and you can also perform ad hoc adjustments. Yeah. So we will see this in a moment. Okay. So in general, workflows, as I said, define the execution order of different services. So, and in the PLANQK platform, we decided to use the workflow language BPMN, which means business modeling notation. This is basically the industry standard for defining workflows. They provide a well-defined stencil set or well-defined graphical representation. So these dots and circles you see, this is this is standard from 2007, and it's still today heavily used. So it makes it easy to communicate about this. There's also a serialization format. That means standardized format how to store this workflows in, which is makes it also possible to port workflows between different execution environments. But it's not so important for this talk here. And as you see, and PLANQK offers now a workflow editor. So with this workflow editor, you can basically design these workflows. Yeah. So for instance, here you see actually a workflow implementation of the scenario I described before. Yeah. And this is a quite straightforward control flow. So the activities here are executed sequentially. This first circle here, it's called a start event. It means this is indicates the start of the workflow, and this one with the at a little bit thicker line, thicker circle, this is called an end event. If this is reached, then the workflow stops. The workflow execution stops, and of course, we cannot just focus on control flow. There's also data flow. Yeah. So with our workflow tool, you can model also data flow. For instance, in this example, we say, okay, the task encode as Kipu gets like a flight matrix. For instance, this could be a JSON file which contains as values all the flights. Yeah? This is just to indicate you have to also to opportunity also with the workflow tool to model more complex data structures. Data transformations between the tasks, because at the end of the day, there need to be also data flowing between the tasks. So, and the good thing is, as I said, this is all part of the PLANQK platform. That means you don't need to install anything or stuff like that. You can use it right away. So, and this is also an advantage compared if we would implement our workflow with traditional programming language. You can easily extend it. Yeah, it's I wouldn't say it's no code, but it's low code, really low code. Yeah. So, for instance, in this scenario, we have here our ISGUI solver at the left side, which is performed on an IBM backend. So, but maybe we decide, okay, let's check how it performs against the INQ solver. So you could also then make here a condition, maybe to decide, okay, which result you take. Yeah, but maybe you let both solvers solve the problems on both backends, and then you decide, okay, the problem is solved by IBM. It's maybe solved in a better way, in a more energy efficient way. So you send it back, and the other problem then is another problem solution is ignored. Yeah, so you can easily. The point here is you can really easily change the behavior of your workflow. So, and this I indicated also before, that at the end of the day, you want to execute the workflow. So PLANQK on the PLANQK platform, this is quite hidden from you, but for the sake of completeness, there's running a workflow engine which executes these workflows. Yeah, you can imagine like it's like a I don't know, a virtual machine or something which reaches this BPMN file or your workflow file and orchestrates then the tasks, executes the service calls, etc. If you have tasks which involve user interaction, which was not shown is not shown example, it's also they also inform users that something needs to be done. For instance, like if a calculation is finished, maybe your user needs to take some action and so on. And the workflow engine is built workflow engines in general, good workflow engines, let's put it like this, are built in a way that they are really resilient. That means they are built that they recover from errors without manual interaction, and that they have already retry mechanisms in place and so on. And under heavy load, they also scale. That means they're using more resources so that you don't need to take care that, for instance, a high demand throttles your workflows.
Sebastian?
And yeah.
Sorry to interrupt. There was a question regarding the classical workload.
Okay.
And the question was, where's the classical workload executed and data stored? Who owns the physical classical hardware infrastructure?
There are different scenarios for this. Thanks, David. You can, with PLANQK, you can either store the data in PLANQK. That means if you have like the classical services, they can store the data in PLANQK, for instance, in so-called PLANQK data stores. Or you can also design your service in a way. PLANQK also supports external service. What this is, these are basically services which are hosted in your infrastructure, and PLANQK just knows about them. Knows how to access them, and you can also use these services in your workflows. So this enables you, for instance, to, if you have business critical data and you say, okay, I don't want to hand them over to the PLANQK platform, that you can maybe anonymize them and then send them to the PLANQK platform. The PLANQK platform is doing the calculations and calls back your infrastructure where you can then continue working. For instance, continue performing your classical computations.
Thank you. And a second question has popped up whilst you were answering the first one, which is more aimed towards the optimizer. And it's good that we also have Jan, our head of development, here in the call. So maybe that's a question better suited for Jan. If a Hubo is given to the optimizer, will the result contain a number of sample bit strings or just one string that minimizes the problem?
Jan still in the call?
Let me check. Here he is. Yeah. We just have to give him the necessary right.
Yes. Okay. No.
There you go. Jan.
Yes. So the current implementation just returns the best bit string. But for sure, we are here open for discussion. So we also have this in our logs, and we can easily, if this is requested by the user, we can easily also extend it to return all bit strings. So this is no issue for us.
Perfect. Thank you for taking care of that question, Jan. And then with that, back to you, Sebastian.
Thank you. Thanks, guys. Okay. So so we are now at a step where we provided our workflow again a service. It is used, and as I mentioned earlier, we also want to monitor it. And therefore, we also integrate the monitoring tool, which visualizes the states of each service. So it shows you the execution state. For instance, here in the example at the right, you see that everything went well, except that storing back the optimized flight routes at the air traffic control, this activity or this task or service, aka service execution, that this failed. So what you can do now is, since you don't want to rerun everything again, you can, for instance, I have to admit this feature is still under development, so this is something I won't be able to show today, but it's under development, that you can rerun your activity or your service. So for instance, here we say, okay, we modify maybe the data before, which might cause the error. Let's assume that these are the data. So we modify the data, and then we run this activity or the service execution. So service execution is executed, and then voila, we were lucky. So our change improved it. So or fixed the error. So you could also imagine, like maybe after the second step, that you say, okay, here the Hubo encoding, there's a small mistake, a small error I want to fix. So you could do this and say then, okay, then I will just want to run the ISCAI solver and the store optimized flight route task or service execution again. So this and I think this is for especially the experimental way we are working in the quantum computing community, really powerful feature that we don't need to rerun everything, but can rerun parts of our experiments or of our business scenarios. Okay. So now let's get our hands dirty. And I will show you a tech demo. So as I said, the workflow modeling feature, the WeHold or workflow modeling feature is quite early. So if there are any hiccups, please beg for apology already in advance. But I am quite optimistic. So for this one, since it's a little bit simpler, we will use a different scenario. What scenario we will use is that we will generate a benchmark, a quantum computing benchmark, execute it on the quantum computer, and then the result is then sent in an email. Yeah, really basic, but I just want to show you the concept. So. And so we create the service orchestration. Yeah, we have different service types. These are on-premise services are the external services I talked about, which run on your data center. Managed services are services which run on PLANQK directly, and service orchestration is just a synonym for workflows.
Okay. Sorry to interrupt again, Sebastian.
Yeah.
There was another question. I think it's quite fitting here because it's around data security, compliance, etc. The question is, what are your specific security, compliance, and data sovereignty requirements when running workloads on the platform?
Good question, Michael. Maybe I forward the question to you.
Yeah, let me try to answer. I think I had the rights to unmute myself. So basically, the platform is designed with that, of course, it runs in the European Union, and it's also the data within the platform is always stored within the European Union. We're of course also improving towards more sovereignty even in Germany, but currently we are, let's say, in the scope of the European Union.
Thank you,
that answers the question.
Yes, I was just saying that. Hope that answers it. Unless or until, if not, then please do not hesitate to ask a follow-up question. And there has been another question: where can we read about the pricing of usage for different kind of quantum hardware? I can actually answer this one. If you go to the PLANQK page or to the PLANQK platform, there's actually a pricing page which lists it out for you for each backend that we offer on PLANQK.
Yes, you can do this here.
Thank you, support.
Exactly.
Then I will hand now back to you.
Okay, so so as I said, the pricing table here at the right corner, you find it. Okay, so let's create now as a PLANQK seminar workflow, and service orchestration type. So the workflow was created, and now this workflow designer pops up. And as you before we go on modeling, sorry, I wanted to show you the service that we will use. This I forgot. We have this service. It's called MQT Bench. This is from the service from the Technical University of Munich, from Robert Willis' team, and they develop basically different services as part of their Munich Quantum Toolkit. This service is the one which can generates basically generates a benchmark. So I don't want to bother you with the details. Then we have another service, which is a backend execution service, which we have already in place. This service basically simply performs sends a custom string to a PLANQK backend. So you can select between different backends, which the backends we are providing are shown here. And you can select the backend and send workloads to it. And the last service is email notification service we will use, is simply sending an email notification to an email recipient. Okay, so now here we have our PLANQK seminar service, and we design the workflow. So, and these are basically the service calls are implemented by this PLANQK service tasks. And I select now, okay, this service task should communicate with this benchmarking service, because at the very beginning we want to generate the benchmark. Yeah. So then in the next step, we want to execute the benchmark on the backend. Yeah. So therefore, we call this backend service, backend execution service. Yep. And in the last step, we want to inform the user about successful execution of the benchmark. So we do this with the email notification service, which we select here. Okay, so now we have the control flow in place, but we also need to model the data flow a little bit. And therefore, 1 second, I have in my the data flow transformations, I have in my notes. Yeah. Exactly. So as you see, this MQT bench service, yeah, we always show how a request to the service should look like. This is like the service has an API description, the API description I was discussing earlier, and the API description contains examples. And based on these examples, it helps you that you know how do the input data look like this service expects. Yeah. So for instance, we need to pass always a data property. So, and we can add this. This was for my notes. So, and this basically says, okay, we're taking a certain benchmark and we're taking a certain circuit size. This benchmark instance name we ignore for now. And so this benchmark here, I could define static value, yeah, then it would take the GHZ benchmark, but I want to at the benchmark, I want to provide a benchmark I want to use when the workflow service or the workflow is started. So I leave this open, yeah. You can imagine this like a variable I pass as input. So, and after we have this, we need to write the output of the service execution, yeah, to the process. Yep. So because the service generates a benchmark, and this benchmark needs to be added, so circuit to the process that the other task can exit it. And here this already proposes you that you should use from the response the CASM string, yeah, because it's defined here. So it assists you also with writing this stuff. So and now the backend the execution of the backend needs an input. Of course, this is the CASM string. So and you see also it must be named data. We make an input here. Data, this becomes the input. We execute it on our IonQ simulator. We keep this hard-coded, and the circuit is the circuit returned by this MQT bench. Yeah? So this is basically the circuit is stored in this circuit variable. Okay. And at the end of the day, we also want to store the result. So we just want to store, for instance, counts result, and take here the counts. It means from the result, don't take elapsed time, just take the counts. And this, in turn, we use as input in the email notification service. So then the input name must be data. This looks a little bit complex. You can ignore this. This is basically what it's doing here. There is searching for the recipient variable. Yeah. So which I will also add set during the execution or the start of the process, and it takes the IonQ execution results, I mean the string, and sends it in a simple message. So if I didn't forget anything, we should be fine. So we can save the workflow. And now, of course, the most dangerous part of a live demo, you need to deploy it. And this deployment, what does it mean? Deployment means that you say, instruct PLANQK to stage this workflow as a workflow engine. So you can imagine like that you say, okay, the service, my PLANQK seminar service, is now implemented by this workflow we just modeled. Yeah. Okay.
Sebastian?
Yep.
There's another question. And we had the question, what tools or APIs enable seamless data exchange between classical tools and quantum workflows?
Good question. You can basically, in PLANQK, we're using REST-based APIs. That means these are basically or mainly JSON exchanges. But you can also, for instance, store data in PLANQK. For instance, your classical tool can store your data in PLANQK on in the so-called PLANQK data store. You can imagine it's like an object store where you can store, for instance, larger data like files, etc. You can with PLANQK also, a PLANQK service can also write files, which you can, for instance, download. Yeah, so this enables basically the exchange between of the data between the services. But you can also do in a PLANQK service, there's no limitation. I mean, you can call your external database. So you can, here in this workflow, the data are basically exchanged in this example simply by JSON flowing between the activities. But what you could also, how you could also implement it, that for instance, this MQT bench service stores the benchmark on PLANQK in some data store or on your private database, and that this service then uses it from there. So there are no limitations. We just help you with interfaces that you don't need to deal so much with this. I mean, we provide REST interfaces, REST APIs. You know this, most of you know this probably, this HTTP GET and POST, but you also see in your browser to query your services. Also to, your services can also write files you can download with our API. So I hope this question is answered.
Thank you.
Okay. And now let's go to applications, our demo app, subscribe to the service. The service subscription, just I forgot to publish it, of course. Yeah, this is an important point. I forgot to publish it. Publishing means make it available to others. Publishing internally means that it's just available for you or your organization. When you publish it in the marketplace, then it's basically available for everyone. Yeah, so of course, since this it's just for our demo, we will just publish it internally. And then subscribe. I need to reload, probably. PLANQK seminar. And then we can start it. And there are different ways to start it. You can start it via Python SDK. Yeah, we offer Python libraries to start the service. You can also start via our job feature. So as job. And I will start it now via the tryout button. That means here you can basically really easily try if your service is working. Okay. Let me check. Just need a good size. Wait, here, perfect. So now I say, okay, use the GHZ benchmark and send an email after benchmarking completed to me. So let's keep fingers crossed if it works.
In the meantime, we have time for another question, actually.
Yes.
Coming back to the question about what kind of APIs, there is the question whether PLANQK also supports stateful APIs.
We support we support stateful APIs in a way that when you call services, the services are called asynchronously in PLANQK. Yeah, I can maybe show you an example. Like go to the services tab. If you have, for instance, the benchmarking workflow service, this API. Do I have an API defined? Unfortunately, not. Second, because I didn't prepare it for the demo. here, for instance, this email service. This you can send an email to. This is a really simple service, but imagine you would call as a service where you call have a long-running operation. Planck provides always this get endpoint, for instance, where you can basically call the result asynchronously, and you see the status of the service execution. So this so you can check, is my service still running? Is it in an error? And when the service state returns completed, then you can return the result basically. So we support asynchronous APIs, but I don't know what exactly for stateful APIs maybe I don't know what exactly for stateful APIs the person who asked the question has in mind. Maybe can clarify a little bit.
Yeah, we do. Maybe you can. We have one more question, but I would like to finalize the demo because we're starting to run over time. And then we'll answer the final question afterwards.
Okay. I started the service. In the application tab, I just now want to check if my Planck seminar workflow worked. So I can check the instance here, and it looks good. So as you see, all activities were executed, and here you see also the variable values. So you see the circuit that was generated by the MQT bench tool, and also the execution result of INQ. And I should have received an email if and there was also just for the demo an email that the benchmark result is available. So so the workflow runs successfully, and beside questions, I would be also at the end of the demo. So, and go maybe back to the slides, and I am happy to answer questions. Sorry.
Thank you so much, Sebastian. Great presentation, great demo. There has been another question with regards to the developer perspective that you have just shown us. And there was a question, what are the advantages of Planck in comparison to AWS Bracket or Azure from a developer's perspective?
From a developer's perspective, is clearly that we have to focus on quantum. I mean, you can in Bracket as well, but in Bracket you are limited to Bracket backends, and you are limited also to the AWS ecosystem. And with our approach, especially with the Planck quantum service approach, you can run services which also classical services. I know it's also possible with AWS, but you have to make an extra effort. So here you can create services which can use different quantum backends, not just the one offered by AWS, but by many other providers. Plus, you can easily set up a service which then also uses classical resources and together with quantum resources to offer your algorithms. And you don't need to, because when you do this in AWS, you also need to make invest effort, like to set up your API gateway at AWS, to think about the deployment mechanism and stuff like this. And this comes all out of the box here.
And I'd like to add on that the advantage of using Planck is, of course, that you can also build applications or services on top of other algorithms, as Sebastian just pointed out, especially, of course, Kipus.
Exactly.
Thank you. A couple of people already left, which is absolutely fair given that we're already 5 minutes over time. I'd like to, again, extend my thanks not only to you, Sebastian, but also the platform development team here at Kipu. You see here the QR code. Please feel free to register on Planck, try out the feature that Sebastian just showed, and please do not hesitate to reach out to us with regards to questions if you want to try it out either as a developer or as an industrial user. We're more than happy to work with you on that. And with that, I'd like to end the recording. Thank you, everybody. Have a wonderful afternoon. See you next time. Bye-bye.
Thank you, guys. And the person with the stateful API can please contact me. I'm curious what she or he has in mind. Thanks.